Hi there, welcome back. I'm Stefan T. Lauwade. I'm a Visual C++ Libraries developer, and my job is to maintain the C++ standard library implementation that ships with Visual Studio. So welcome back to the second part of this introductory series to the STL. In part one, I introduced the basic overall layout of the STL and its sequence containers. So we saw the sequence containers, vector, and I believe I mentioned dec, list, and I may have mentioned forward list in passing. This one is new to Visual Studio 2010. So vector is the sequence container of first resort. It's the one that you should be using almost all the time. The others are much more specialized. Sometimes people use list because it has a nice sounding name, but in fact you don't want to use doubly linked list most of the time. Vector is the most efficient and the most useful one for the vast majority of applications. So as the title may indicate, sequence containers, they remember a sequence of elements. If you've got a vector of int and you start pushing back ints 11, 22, 33, 99, and 44, they remember the order in which you pushed back those elements. That's often what you want. A vector can be thought of as a flexible array. But sometimes you don't want a sequence container. Sometimes instead what you have is one element, a key, perhaps a name, and you want to be able to, given that key, look up some piece of data associated with it, what we call the value. And for example, a phone number. Or any other mapping you could think of. This is a very broadly useful idea. The STL has containers for them, and they're called the associative containers. Now, a little bit of terminology here. Many other languages will refer to these as hash tables, because that happens to be how their associative containers are implemented. If you look at documentation on the STL, you'll actually notice that hash table is not what is used to refer to most of these, because the ones that shipped in the original STL, C++ 9803 in Visual Studio 2008 and earlier, they were not implemented with hashes. Instead, they were implemented with a different data structure that I'll be going over. So the STL terminology is associative container because they associate a key to a value. And the associative containers are map, multi-map, set, and multi-set. So, for associative container sounds like a lot to learn. In fact, they're all really the same thing. In fact, they're all backed by the exact same data structure. It just depends. The differences between them are what elements they're storing. Map differs from set here, and whether they permit duplicates or not. That's where the multis come in. So once you've learned one of them, you basically know how all of them work. So forward list, this is C++ OX. These ones are C++ 9803. In C++ OX, we got some new containers called unordered map. And same for unordered multi-map, and unordered set, and unordered multi-set. I'm abbreviating here. It's actually spelled out multi-set. So, and these are all C++ OX in Visual Studio 2010. Yay. Happy face. The unordered containers, as the name says, don't automatically sort their elements. What this really means is that they actually are implemented with hashes. The reason why the standardization committee didn't choose the name HashMap is because that name had already been chosen by many non-standard implementations, including Visual Studio's own. You shouldn't be using those anymore. Now that unordered map and multi-map and so forth are in the standard and in Visual Studio 2010, use those. Their interface is actually better than the non-standard HashMap implementations you'll find floating around. So I actually prefer to introduce the ordered containers, the C++ 9803 containers map and set first, because they're a little simpler to understand, and they have more predictable behavior, and I find them easier to use. The unordered containers are useful, when you need their performance and complexity guarantees. But overall, they all share basically the same interface, which is pretty convenient. The STL, in addition to being partitioned into sequence and associative containers, also has what are referred to as container adapters. These are stack queue and priority queue. And in particular, priority queue kind of looks like map and set because it's automatically sorting, but it's really just a layer over the sequence containers. I may get to that if I have time. So first, map. Map is, with vector, one of the containers that when you're using the STL, you'll probably be using all of the time. Set is useful, some of the time. The multi-container is actually not so commonly useful, but when you need them, it's great to have them. So what map is, of course, just like every other container in the STL, it's templated on its element type. Unlike vector, which is templated just on T and its allocator, which I won't go into, map is templated on two types, its key and its value, and the key comes first. So if you look at what I've got here in Visual Studio, I've got a map from int to string, that's just how I pronounce it, that I've called M. So this first type int is the key type that I will be giving to the map in order to look up the value associated with that key, in this case a string. Oops, I didn't mean to move that. So using a map is actually quite simple. If I want to insert things into a map, there's a syntax to do that. It's actually with square brackets. So I could say m of 1 equals 1. And then m of 2 equals 2. And I can put things in any order. I could say m of 4 is 4. M of 3 is 3. And then I can start looking up things. So I could print out whatever m of 2 is. And now that I have a larger console font, thanks to your feedback, you should be able to see what's going on here. Oh, I'm also hiding, of course, declarations to print out. I need IOStream and OStream. Map lives in the header map, and of course I need string. All of these sequence containers live in the header that is identical to their name. With the associative containers, both map and multi-map are defined in the map header, and both set and multi-set are defined in the set header. There's no multi-set header or anything. Similarly, with unordered map and unordered multi-map, they live in the unordered map header and so forth. So that's why I'm including them. And if I execute this program, when I look up the integer 2, I'll find a std string, and I'll print out in letters the word 2. So if I execute, well, first I have to build, and here we go. Yes, it printed out 2. So this is showing that I can associate keys with data. And then I can also update them. So if I chose to, let me stop debugging. Later on, I could update things. Of course, this is a highly artificial example. Real usage doesn't look anything like this. I could then update this in place to make it say all capitals, like this. And because I'm printing out m of 2 after I've updated it, I will get capital 2 with an exclamation point. So this can be extremely useful. One issue with explaining the STL is because it is this generic tool, there are so many uses you can put it to. Things like sequence containers are useful in every application. Similarly, for associative containers, they could be associating, if you're drawing objects, it could associate a layer with a pointer to a model to draw onto the screen. It could associate IPs with a client connection. It could associate a name with a handle to a font, anything you can think of. As long as they're OK to be used as elements of an STL container, you can put in a map. So my examples, because I don't have time to create a whole application that draws something on the screen with fonts and all that, they're just going to use things like int and string. But hopefully you should be able to imagine all of the uses that you can put these data structures to. So this is the very simplest usage of map. I mentioned that map is actually ordered. What it's doing is it's automatically sorting its key value pairs. So let me actually, I can leave it like this. Instead of going and printing out a particular element of the map, I can iterate through it. Just like the sequence containers, the associative containers have iterators, and this can be used to iterate over all elements of a map instead of looking up particular keys. And because map is automatically sorted, I will get some convenient output. So I'm going to start iterating for, and I'm going to use C++OX auto. If I wasn't using auto, I would have to type map of int string, I can't type, double colon iterator. Or if I wanted to only inspect elements, I would say const iterator. But this is verbose, and in 2010, I can now get rid of this and simply say auto. For auto I is mbegin, as long as I is not mend, and ++ I. And because I don't need to modify the container, I can explicitly request constness. This will give me a const iterator that I can't write to the container through. You'll notice that this loop looks exactly like the loop that you would use to iterate through a vector, even though it's traversing a very different data structure. This is the power of the STL, as I would usually say. The fact that once you learn how to write one iterator loop for a vector, then you can apply that to things like forward list, map, multi-map set. It all works. You don't have to learn a whole new syntax. And then I can print out the element. So the elements, if I've got a vector of t, its elements are of type t. So vector int, if I dereference an iterator to a vector, I'll get an int. With map, if I have a map, I can erase the sequence containers now. If I have a map from int to string, its element type is pair of const int string. Pair is another helper class defined in the header utility that is used throughout the STL, and in particular used by map. Pair is what is really the simplest class in the world. It has two elements, dot first and dot second. So because map is mapped from key to value, the first element is the key and the second element is the value. And the key is const because you cannot be permitted to modify keys in place. That would break the data structure's invariance, corrupt your program. Not good things would happen. So as I'm iterating through the map, I can print out both the key and the value associated with it. So I could, for example, print a parenthesis and then the iterator. Now this iterator is of class type, but because it imitates a pointer, it not only overloads operator dereference, but also operator arrow. So just like a pointer, I can say iArrow to access a member of what that iterator points to. And here autocomplete is actually reminding me that it points to a pair. So I can print out the first element of that pair, which is the key. And then I could print out a comma, and then I could print out the second, which is the value, and then say a parenthesis, and then a new line. I could do this in reverse order too, put the value and then the key, but I'll keep things simple. And then if I run this, what will happen is the map is not only associating keys with values, but it's also sorting them based on the key. And the default sort, as usual, is less than. So I'll print out the keys in ascending order. Even though I inserted these key value pairs in the order 1, 2, 4, 3, they'll be printed out in sorted order, 1, 2, 3, 4. And of course, this update will be reflected in the map. So if I execute this, what I will get, build succeeded. Come on, run. There we go. So I had inserted this into the map, and what I get printed out is the keys go in the order 1, 2, 3, 4, regardless of the order that I had inserted them into. So this demonstrates how map is automatically sorting its keys and values. This can be very useful if you need to be inserting elements into a data structure and have it continuously sorted. And I can access both the key and the value in addition to looking them up. So a little bit about how map is implemented. We can see its interface here. It's never good to know too much about an implementation if you don't need to know those details, because then you start making assumptions that you shouldn't, and when those assumptions change, when the implementation changes, your code will be broken. But in order to understand the complexity guarantees of things like vector and map, it's useful to have some vague idea of how they're implemented. So the way that a map, I can erase this now, say from int to string is implemented, is it's a balanced binary tree. So you can imagine that my map looks something like this. There's a root. It's balanced, but not perfectly balanced. And each element of the map is a pair from const k to v. And as I insert elements, this tree, which happens in our implementation to be a red-black tree, you can look it up in your favorite computer science textbook. What happens is that I'll allocate, say, a new node. Say I just inserted the key 4 and the value 4 string. I will get a pair saying the number 4 and the string 4. And this pair will be, I'll get a node containing that pair and some pointers. I'll insert it into the tree in sorted order and then rebalance the tree so that its invariants are maintained. So what map is doing is when you insert something, because the tree is being continuously balanced, the insertion is guaranteed to be logarithmic time. So if I have 1,000,000 elements, then that insertion will take on the order of 20 comparisons times some constant factor to insert and rebalance that tree. If the tree expands to 1 billion elements, the insertion will only take some time proportional to 30. So log n is extremely fast. It's not quite constant time, but it's the next best thing. Also erasure, if I need to look up a key and remove it, then it's also logarithmic time. And this is guaranteed. It can never get worse than that. This is an extremely useful guarantee, and it means that in practice, map is quite fast. If I want to traverse every single element of the map, well, of course, there's n elements, so that is going to take linear time. It does a depth first search, so I'm going to iterate through each element like this, and I can walk the whole tree in constant time. So if I do iteration from start to end, from begin to end, iteration. Of course, that's order n. It can't be any faster than that, but it's nothing like n log n. And of course, destruction is linear time because you have to go destroy every single node. So overall, you can think of map as a very efficient data structure. So here I have demonstrated using operator bracket bracket and iterating through. Now, unlike vector, map's operator bracket bracket has a secret, and that secret is that it's actually modifying the map. Notice how when I construct this map, it has no keys and no values. It's empty. I could call .empty and that would return true. And then when I said m bracket 1 equals the string 1, I inserted an element. This is completely different from how vector behaves. If you remember from part 1, I demonstrated that when you had a vector of, say, int, and the vector started off empty, and then you started just saying v bracket 5 bracket, the vector would crash because the vector was empty and you try to get its element number 5. If you want to insert elements into a vector, you need pushback. With map, its operator bracket bracket works differently. What this is doing is if I have a map, say from int to string, and I use operator bracket bracket on that map, what this returns is an int reference. Sorry, I got that wrong. If I give it an int, because the key is of type int, it returns a string reference, because that's a value type. What it's doing is it's going to do a lookup. It's going to say, okay, does this key exist in my data structure already? If it does, then it says, great, I'm going to go find its value and return a reference to it. Because it's a modifiable reference, I can then assign or otherwise modify that value in place. This is what lets me say down here, m bracket 2 bracket equals 2 exclamation mark. Because this element already exists in the map, I get a reference to it, and I can refer to it in place in the data structure, the value part. If it does not yet exist, for example, here, when I said m bracket 4 bracket equals 4, the map says, oh, you tried to access a key and it doesn't exist. I'm going to create one for you. So it will insert a new node, logarithmic time, into its data structure with whatever key you provided, and it will default construct, or zero out in the case of something like an int, a value. So if I simply said m bracket 4 bracket without any assignment or anything, I would get an empty string associated with that 4. And what I do is I get a reference to that newly inserted value, and then I can go assign to it. So this is very convenient syntax, but it can be surprising. If I had a function taking const map in string reference, I would not be able to use operator bracket bracket. Actually, let's see what happens if I try to do that. Maybe I have a function void foo that takes, I don't want to see these declarations. Hey, where'd that go? Oh, it's not yet aware that I have a function definition. Const map int string. I could use a type def for this, and I probably would if this type were more complicated. M. Say I tried to say m of 7 is 7. Like this. And then down here, I could call foo with m. Yes. So this is an attempt to modify the map, but I took it by const reference. So if I attempt to actually compile and execute this, I will get a build error. Edits were made which cannot be compiled. Click edit to fix the code. So I'll get an error list that says, now, interpreting STL errors, as you saw in the comment thread to part 1, can sometimes be difficult. The compiler is trying its best to report exactly what went wrong. In this case, it says binary bracket, no operator found, which takes a left-hand operand of type constd map k type, or there is no acceptable conversion. What the compiler is trying to say here is that you are attempting to call a non-const member function on a reference that is const. Maps operator bracket, because it can insert a new element, is not marked as const, which means that you can't call it in this case. So this will fail. Now, this should fail because I'm trying to modify the map. Imagine that I simply wanted to print out m of 7. So I'm taking a const map reference, and then I simply want to see, actually, because I have elements like this, say I want to print out m of 3, this will also fail to compile. This is what will confuse you if you haven't seen this before. If I try to build this, I will get the exact same error. It will say, hey, again, no operator found, blah, blah, blah. Even though here it looks like I'm only interested in reading the map, and that should be okay because it's a const reference, remember that maps operator bracket can insert that element, and it is secretly modifying. So if I want to be able to read a map, I can't use read through a const reference. I can't use operator bracket. Instead, I have to use find. So here I can say map in string, and here I must say const iterator because that's what I'm going to get back. I is m.find of 3. And because I have C++ OX, instead of saying this thing, I could simply say auto. It's the same type. It's still a const iterator. And then I can make sure if I is equal to m.end. So so what find takes is a key. In this case, the type is int. If the key is not found, what the STL will do is return the map's end iterator. It's a convenient iterator that doesn't point to anything, and it's a sentinel value that says, I didn't find what you were looking for. So if I is returned and it happens to be mend, then what happened was that key was not found. Now, I inserted a key of this value, so I do not expect to see this at all. Otherwise, so if I were writing this in production code and I knew that this key had to be there, I would replace this with an assertion, a check that would say in debug mode, if I don't find this, I want to kill the program dead. In this case, I'm just writing this code as a demonstration. I expect this branch to be taken where I is not equal to mend. That means that I can dereference the iterator. I can print that out. Cout I arrow. I just want to print out the value, second. Because find says, hey, I'm only looking at this map. I'm not trying to modify it. It's marked as const. And that means I can call it on a const reference. Let me move this down. So this code will compile and execute. And in addition to inserting all of these values, it will print out 3 in words. So if I compile and execute, here we go, run. And it prints out 3, exactly as I expected. So you should use find when you want to look up values in a map without modifying it. This is sort of the first gotcha that gets people when they're using map. So I had listed, let me erase some of this, the 4 associative containers in the original STL, which are map, multi-map, set, and multi-set. Map is special. Map is the only one that has operator bracket. The other containers do not. With multi-map, the reason is a little surprising. You might think, oh, if I can have, what multi-map permits is having one key being associated with many values. what map does is it enforces a one-to-one mapping. If I have a key, like the number 3, I can only associate that with one value. I can put any string there, but only one. I can't say the number 3 maps to the string 3 and the string, capital 3, something like that. Map will not permit this, multi-map will. However, multi-map does not have operator bracket bracket because if a key were associated with multiple values, remember that this has to return a reference, a value reference. Which one would it return? Is it going to return the first one that happened to be inserted? Is it going to return something that somehow refers to all of them? Instead, it says, I'm just not going to have operator bracket bracket. If you have a multi-map, you need to use member functions like find, lower bound, upper bound, equal range in order to access and look up its elements. With set and multi-set, they're just like map, except that they only have a single type. They're templated on T like this. They're not associating a key with a value. So that means that they don't have an operator bracket bracket that would take a key and return a value. So these 3, multi-map, set, and multi-set, they have all of the same member functions really as map, like find and lower bound, but they don't have operator bracket bracket. So that's sort of the special case there. I had mentioned set. Set is a little less useful than map, but what it's doing is it's got the same tree structure, same logarithmic time guarantees. You can think of it just as an automatically sorted container that enforces uniqueness. So suppose that I have a set of int, and I can say the member function for the set would be insert. Let me give it a name. S. I could say s.insert, and I want to insert the number, 33, and then I could say also s.insert 1729, and in any other numbers that I like in any order. What the set will do is this is a mathematical set really. It will contain 33, 17, 29, 11, any other numbers that I put into it, and they're going to be automatically sorted. So if I start iterating through the set with its begin and end member functions, they'll be printed out in sorted order. Again, the default comparison is less than. And set will enforce uniqueness. So if I try to insert 33 again, what set will say is, oh, I already have a 33. I'm not going to insert it because I only want to store 1. If you have a multi-set, it'll store multiple copies. This can be useful in some cases. Imagine that you need to maintain a set of file names that the user has touched, or a set of names, and you need unique names that have been entered, and you want to be able to look them up. The other thing that set does, in addition to automatically sorting, is permits log time lookups. You can imagine using a vector. You could say, oh, I'm going to have a vector int, I'm going to push back things, and then if someone wants to look them up, I'll do a find. But remember that vector find, because vector is a sequence container, is going to be linear time. If the element that you're looking for happens to be at the end of the vector, it's doing a find on a vector will not find it until it's looked at every element. So in the worst case, it could be linear time. Whereas set and all the other associative containers are going to guarantee log time lookup. That's extremely useful, much faster than linear time. So you should use the data structure that's appropriate for whatever application you're doing. So I had mentioned the unordered containers. I can briefly demonstrate them. Let's get rid of this here. I would need to include unordered map, this header. This is actually, because it's part of C++ OX, it originally came from TR1, the set of additions that we added to Visual Studio 2008 Service Pack 1. So if you're running 2008 SP1, this header will be available to you. It happens to live in the namespace stud:/TR1. So here I would, after including unordered map, I would say unordered map here. I'm not going to rename it. And I can do exactly the same things. It happens to already have a hash for int. So I will actually get rid of foo here, and I can simply, let's just print out something, m of 2, and L. It has basically the exact same interface. It has a few more functions, things like max load factor and bucket count that are specific to the unordered map implementation, but things like find, lower bound, and operator bracket bracket are on unordered map, just like the ordered std map. So I can save and compile this, and oops, I made a mistake somewhere. What did I do wrong? Unordered map and string. Okay, let's look at my error list. Edit and continue. Oh, it's got some edit and continue problem. There we go. Let's start a build from scratch. There we go. Nothing was wrong with my code. And let's start this up, and it works. So unordered map has exactly the same interface as ordered map, but the data structure is very different. So I can sketch this out real quick. If I have a map from some key to value, then it's a balanced binary tree. Happens to be a red-black tree in our implementation, and really every implementation I can think of, that associates these pairs of keys and value. Now, if I have an unordered map from key to value, this is a hash table. You may be familiar with that term. And it's doing a lot of magical things, but you can basically think of it as it's going to hash the key and have a chain of buckets that have special numbers. These are these hashes. If I hash one key, I might get a number like OX45AB, and then just some pseudo-random hexadecimal value. And this bucket, these are buckets, will be associated with a chain of values. V, V, V. The difference between unordered map and map is that you can have hash collisions. Different keys may generate the same hash. That's why these buckets need chains. There's many possible implementations of hash tables. We happen to use one. Doesn't quite look like this. I'm omitting some details here. But the characteristics of unordered map is that if you insert into an unordered map, it's expected to be constant time. Basically, you take that key, you hash it, you get the pseudo-random hexadecimal value, you find the bucket, and then you append it to the end. However, in the case of hash collisions, it could be worse. It could be worst case order n. Same with erasure, same with lookup. If your keys are, through random chance or perhaps maliciousness, creating these hash collisions, the performance of the unordered map can degrade. This is very different than the ordered map, which guarantees log time. It's impossible to make ordered map misbehave because that tree is just going to automatically rebalance no matter what you do. So the idea behind unordered map is that it will actually be faster most of the time, but in certain scenarios it could potentially be slower. I actually recommend using ordered map as your container of first resort when you need associative container, simply because its interface is easier, less typing, and in particular it's templated on a comparator. So if I want to customize how the map is sorted, I can give it a comparator after the value here. And this is a comparator just like we saw in part 1, such as given to std sort. It needs to compare two elements for less than-ness, and as long as it behaves like less than, it can do whatever it wants. So comparing by greater than is a perfectly valid comparator. And here I could, actually this is important enough to demonstrate. Let me go back to my ordered map. If I have my ordered map here, and let me get that loop that prints out everything for auto I is m.cbegin, as long as I is not m.cend, for increment I will print out, I'm not going to bother with those parentheses, I arrow first, space, I arrow second, and L. So this will be printed out in, as I mentioned, sorted order, sorted by less than. So I will get, let's edit and continue again. I will get them printed out in the order 1, 2, 3, 4. Now imagine that I wanted to customize the sorting order. Perhaps it's crucial to me that I get them printed out in descending order with 4 coming first. Well, I need the functional header if I want a comparator that has already been implemented for me. Functional. And map has an extra template parameter, the comparator, and here I want to compare the keys, which happen to be int, by greater than-ness. So I give it greater int, and what this will do, let me stop execution and run, they get printed out in reverse order. So you can see here that exactly the same code, all that I've done is change the comparator, and now they're getting printed out in the order 4, 3, 2, 1 because the comparator greater int has been used. So customizing a map is very easy. It's usually quite easy to write a less than comparator for whatever your element type may be. With an unordered map, you need to provide a little more. You need to provide a good hash function, one that does not produce lots of collisions, and you need to provide an equality predicate because the unordered map needs to know when it's found the right value. That's two function objects that you have to provide compared to one, and it's a little harder to write good hash functions. So it's certainly not impossible to use, but for ease of use and because it guarantees performance, I always suggest starting with the ordered map and only use unordered map if you find that performance requires it. So that's the associative containers. I did want to mention something important about the sequence containers. So imagine that I've got a vector, int v, and I start inserting elements like I did last time. Okay, say I've got my elements 11, 22, I can't spell, 22, 33, 44, 55, and I then want to start removing elements that I don't like. Now, perhaps I just don't like odd numbers and I want to eliminate 11, 33, and 55. But of course, in your application, it could be you have a vector of sockets and you want to eliminate all of the ones where the client is disconnected. You have a vector of enemies in your game and you need to remove all of the ones that have 0 or fewer hit points, whatever it happens to be. You just have elements that you don't like and you want them gone. This actually requires something non-intuitive to do. It's called the erase remove idiom. So if I bring up a vector, I'm just going to add in the header here. There are many wrong ways to do this, and one good way. I'm also going to need the algorithm header. Suppose I've got that vector int. Unfortunately, VC10 does not have initializer lists, so if I want to push back a bunch of integers, I need to say this instead of braces, which would be very convenient. Let me copy and paste this a little. I could use a for loop, but that would take a little bit to write. 22, 33, 44, 55. Now, if I want to remove all of the elements, you may be tempted to go look up, say, an MSDN or the standard or your favorite C++ textbook, vectors member functions. And you'll find one called erase that has a suggestive sounding name. And you can use it with an iterator to erase a single element. You may be tempted to write a loop which individually erases all of the elements you don't like. This is actually horrible. Not only for performance, but also for correctness, because almost everyone gets this wrong when they try to do it. Ignoring the correctness issue, people will invalidate their iterators. I'll have to get to iterator invalidation in a future part. Imagine that I've got my vector like this, and I start removing individual elements, and I start iterating through like this. So I say, okay, this element, oh, it's odd, I don't like it. Let's erase this individual element. What the vector will do, because it needs to remain contiguous, it's a contiguous sequence container, it's going to shift all of the elements that it has back to fill that gap. So it's going to do a linear time pass and assign 22 here, 33, 44, 55, and then it's only going to be a vector of length 4. And then I say, oh, I like 22, wait, I don't like 33, erase this, and the vector will again move everything back, and I'll get 22, 44, and 55, and so forth. Now, if you look at all of the assignments that it's doing an erasure like this naively is quadratic time, order n squared. And as we saw in part 1, quadratic time is really bad if you can possibly avoid it. And in this case, you totally can. So don't write loops that individually erase elements from a vector. Instead, what you have to do is use what's called the erase remove algorithm. So this is two parts. First, you use remove, and then you use erase. This has to do with how the STL is arranged, as I mentioned in part 1. The STL has a partition between the responsibilities of containers and the responsibilities of algorithms. Containers care about things like their size, how many elements they have. They manage the memory used to store those elements, whether it's vectors, contiguous block of memory, or the nodes in a map, or whatever you have. They're not so interested in what you're doing with the elements. That's what algorithms are for. STL algorithms are non-member functions that work on elements through iterators, thereby not knowing too much about the representation details of containers. And in particular, you need this when you're erasing elements from a vector. So using the algorithm std_remove or std_remove_if, this is a non-member algorithm. What this does is it will take your vector, say I've got that 11, 22, 33, 44, 55, and it does a linear time single pass. And what it will do is basically maintain 2 iterators and compact the good elements down. So it'll say, okay, 11, I don't like that. 22, I do like that, and it's maintaining 2 iterators here. So it'll write 22 here. And then it'll say 33, don't like that. 44, ooh, this is a good element, let's keep it. Let's write it here. 55, don't like that. So it will assign the good elements, the ones you want to keep, to the beginning of the vector, and it will return an iterator to the end of the good sequence. The remaining elements here are left in some unspecified state. They could have their original values, they could be empty. Sometimes we'll use move semantics. You should not look at their values. Now, because std_remove is a non-member algorithm, it cannot actually change the size of the vector. It only sees iterators. We saw in part 1 why this is great, because separating the responsibilities of containers and algorithms avoids code duplication. But in this case, that means that we have to do a little extra work in order to actually change the size of the vector. That's what vector erase is for. This is a member function of the container, and what it will do is it will take that iterator given by std_remove and say, okay, I want to erase a range of elements, and that's how you deallocate this from the vector. In this case, it's actually not going to do any memory allocation, and you'll be left with a vector of 2 elements, 22 and 44. If you read Scott Meyer's book, Effective STL, he calls it the erase-remove idiom, which is as good a name as any. And the way that I use it is I need to say v.erase, and in this case, I'm going to call std, I've got a using namespace std up above, remove if, this is from the algorithm header, and I need to pass a range. Here, IntelliSense is telling me it takes first, last, and a predicate. So vBegin, vEnd, and then my predicate, I'm going to use a lambda. I could write a handwritten function object, but I have Visual Studio 2010, so I'll write a lambda. It's going to take individual elements of the vector. Remove_if will be passing the elements one by one, and it will return whether that element is bad. Remove_if wants to know if an element is bad. So I'm going to return whether that element modulo 2 is equal to 1. This will return whether the thing is odd. And remove_if will then execute this algorithm and compactify the good elements. And what it will do is return an iterator to the end of the good sequence. So in this case, it's going to return an iterator here. This is what remove_if is returning. Now, vector has a couple overloads of erase. One is that single iterator erase that you really don't want to use unless you absolutely need to. In this case, you don't. The other overload that it has is a 2 iterator overload that takes a range of elements to erase. In this case, we want to start erasing here and go all the way to the end of the vector and erase all of those elements. So after calling remove_if here, this is the first iterator to pass, and then I'm going to pass v.end. This is actually a gotcha. If you forget to pass v.end here, you will call the single iterator form of erase and snip out just one element, just this one. And it will compile and execute silently because it's perfectly valid to call that overload. You really don't want to do that. So this is the first thing usually that I write a non-member function to do, to take a vector and, in this case, take a predicate and both call erase and remove_if and remember to pass the second iterator to it. And then I want to simply print out the vector. So I can for auto I is, whoop, I hit end. I is vBegin, I not equal vEnd, plus I, print out each element of that vector. There's other ways I could write this with a for_each algorithm or a copy to OStream iterator, but this iterator loop is pretty simple. Oh, and I need to dereference this. Thank you, squiggles. And this should work. So the vector, actually I can just copy this loop and show you what happened before I called erase remove. The vector starts off containing 11, 22, 33, 44, 55. I execute erase remove to both erase and remove all of the odd elements. I don't like those odd numbers, and then print out the vector again. So I'll get just 22 and 44. So if I execute this, build succeeded, and my program prints out, oh, I didn't put a divider here, but it prints out 11, 22, 33, 44, 55. Erase, remove, executes here, and then I get 22 and 44 as I expected. So this is the correct linear time way to erase all of the elements that you don't like for a vector. If you get tired of typing all of this out, you can write a non-member template function that works for any vector and takes a predicate and will execute this for you without the danger of forgetting that second v end. Erase, remove also works for std_dec, which is a random access container. For std_list and forward_list, there is actually a member function erase that is more efficient because it can simply erase individual nodes in place. So the first of your homework assignments that people requested in the comments to part 1 is write these non-member template functions for vector, dec, list, forward_list that erase elements that you don't like, either values or based on a predicate, with the correct implementation, and also implement that for map, multi-map, set, and multi-set. You'll need a completely different implementation for those. There you can't call erase remove because that would attempt to modify elements in those data structures in place. That would break the data structures invariants and will fail to compile and would be completely horrible. And curiously, they don't have member functions that allow you to erase all of the elements that you don't like. But every once in a while, you've got a map and you need to purge that map of either keys that satisfy some predicate and therefore can't be looked up in log time, or based on the values or some combination of the key and the values. There you actually do need to use the single iterator form of erase. So as you write this loop, remember not to invalidate your iterators. You can look that up in your favorite STL textbook. I'll be covering that in the next part. This homework is sort of a preview for that. And once you've gotten overloads of this helper written, you can call it whatever you like, then if you pass it either a vector or a map or a set, the right implementation will be selected thanks to overloading. So that should teach you a little, hopefully, about iterator invalidation, how to use map, how to write iterator loops by hand. In fact, you will have to use, if you don't use auto, you'll have to use type name, which is interesting. And it shouldn't take you very long if you get the implementation correct. So come back next time when I'll be talking about at least iterator invalidation, because that is a big topic that generates lots of confusion, and whatever else that you would like to hear about. So leave a note in the comments if you have any questions, and I'll try to address that in part 3. Thank you for watching.